In the next set of videos, we're going to take a look at acid-base titration. So what happens when you react an acid with a base? Try to neutralize either the acid or the base, whichever you're starting with. All right, so before we get to that and talk about how we solve titration problems, we need to review what we know so far about water, strong acids, strong bases, weak acids, and weak bases. Okay, so let's first start with some pure water. So the equilibrium reaction for this is the autoionization reaction where we have 2 moles of water is in equilibrium and forms H3O plus and hydroxide ion. Okay, so this is the reaction. Which way is the reaction going in this reaction? Well, it's going to the left. And the first question, how do you know that? Well, remember that Kw for this reaction is 1.0 times 10 to the minus 14th. So if K is less than 1, that means it's favoring reactants. Okay, so that's how I know it's going to the left. All right. Now, if we have a strong acid in water, like for instance HCl, okay, HCl reacts with water, and even though it's going to form an equilibrium, the reaction is going to lie all the way to the right hand side. So you're going to form H3O plus and then your conjugate base. But like I said, the reaction is going to lie all the way to the right, okay, and you're almost going to get almost virtually 100% dissociation. Okay. All right, so the equilibrium constant, the value, Kc or Ka, depending on which one you use, is large. So it's going to be definitely, Ka is going to be definitely greater than 1. Okay, so it's for sure going to lie towards products. All right, well, what about the strong base in water? So, if we take like a strong base like sodium hydroxide and we dissolve that in water, we're going to form sodium ion and hydroxide ion. Okay, so that's our reaction. Which way is the reaction going? Well, this is also going to go towards the right. So even though this, we could set this up as an equilibrium, the reaction is going to lie all the way to the right. So it's going to favor product formation. So Kb for this reaction is also large. So in this case, Kb is also going to be greater than 1. Okay, so first conclusion we can make before we go on is that for a strong acid or strong base, you only need to consider the water equilibrium. All right. What about weak acids and weak bases? Let's take a look at weak acids. So the equilibrium for a weak acid, let's say I take an acid and react this with water. We're going to form a conjugate base, but it's going to give us H3O plus, and that's the most important thing. The acid plus water is going to yield our conjugate base plus hydronium ion. So in this reaction, which way is equilibrium going? It's actually going to the left. So the Ka value for this reaction is going to be definitely less than 1. Okay, so it's definitely going to be low. The equilibrium expression for this Ka would be the concentration of your conjugate base times the concentration of H3O plus divided by the concentration of the initial acid. Okay. Now, if you have a weak base in water, that reaction would look like this. Your base plus water, your water would act as an acid this time. You're going to form an conjugate acid plus hydroxide ion. And so this is what is going to separate. This is what the weak base reaction will do. It will form hydroxide ion. Now, which way is the reaction going? It's still going to the left, just like the last reaction. So the Kb for this reaction is going to be less than 1. And so the Kb expression for this reaction would be that you have the concentration of your conjugate acid times the concentration of hydroxide divided by the concentration of the initial base. Okay, now if I was to combine the last two reactions, okay, so if we take acid plus water is in equilibrium with base plus H3O plus. I think you guys know where this is going to go. And we measure Ka for that. And then the second reaction was base plus water is in equilibrium with acid plus OH minus, and we use a Kb for that reaction. If we add these two up, the acids will drop out, the bases will drop out, and we get that 2 moles of water is in equilibrium with H3O plus and hydroxide ion, or Kw. All right, so, and we know that the relationship between these two, Ka times Kb, will also give you Kw. Okay, all right, so using the generic acid, right, the chemical equilibrium for the neutralization reaction between a weak acid and a strong base. So what I'm saying is this: we take acid plus hydroxide ion. What do we get from this? Well, acid plus hydroxide. The hydroxide is going to take a proton from the acid, so you're going to form a conjugate base, which is going to be negatively charged, but you're also going to form water. Okay? So in this case, which way is the reaction going? Well, this hydroxide ion definitely wants to pick up the hydrogen, and you're forming water. So in this case, the reaction is definitely going to the right, and the value of the K constant is going to be large. It's going to definitely favorable. It's definitely going to favor product formation. Okay. Now, how is this going to be related to the previous Ks? Because remember, this reaction is pretty much the reverse of what we've done right here. So the product, your reactants are now your products. Okay, and your products, your reactants. So how is this going to be related? Well, this new K that we're looking at, this is going to be proportional to 1 over the Kb value. All right. Well, what if we go the other way? What if we worked with the generic base, okay, and we react that with H3O plus? Let's see how that works. So the H3O plus, so the base is going to take a proton from H3O plus, so you're going to form an acid, but you're also going to be left with water. And even though an equilibrium will set up here, you're going to favor product formation because you're forming water. Now, so which direction is this reaction going? It's definitely going to the right. What value is the K constant? It's going to be large, and it's going to be greater than 1. Now, how is this going to be related to one of the previous Ks? This is because this is the reverse of the Ka reaction. This K for this reaction is going to be proportional to 1 over the Ka. And so what conclusion can we draw regarding the neutralization reactions? So both reactions are going to the right. So they're both going to the right. And then K will be something like this. If we take 1 over the Ka times 1 over the Kb, this is going to be equal to 1 over the Kw. Now, you may be asking, when we wrote the two neutralization reactions, why am I reversing these reactions? And there's actually a really good reason for that, which is something we're going to talk about in the very next video when we talk about a first titration.